Welcome! In this session, we'll dive into LeetCode problem number 1908, titled Game of Nim. This is a fascinating problem grounded in combinatorial game theory, where we explore if the first player can secure a guaranteed win. Let's get started. In the game of Nim, two players compete by taking turns to remove stones from several piles. The objective of the game is simple: the player who cannot make a move loses. You're given an array called piles, where each element represents the number of stones in a specific pile. The task is to determine if the first player can guarantee a win, assuming both players follow an optimal strategy. Here are the rules: on a player's turn, they can choose any pile and remove at least one stone, or as many stones as they want, up to all the stones in that pile. If all the piles are empty and a player has no move left, they lose. The challenge is to decide whether the first player has a guaranteed winning strategy, given these rules and constraints. The output for this problem is a Boolean value, either true or false. If the first player has a strategy to guarantee a win, the output should be true. Otherwise, it should be false. Let's look at an example to clarify. Imagine you have a single pile with just one stone, represented as piles equals 1. Here, the first player can simply take the one stone, leaving no stones for the second player. Since the second player cannot make a move, the first player wins, and the output is true. This example highlights how the first player can guarantee a win when there's only one pile with one stone. Now consider a slightly more complex example with three piles, each containing one stone, piles equals 1, 1, 1. In this case, the first player can only take one stone from any of the piles, leaving two piles with one stone each. Then, the second player can take one stone from another pile, leaving just one pile with one stone. The first player is forced to take the last stone, and now the second player has no stones to remove, making the first player lose. Thus, the output for this example is false, as the first player cannot guarantee a win when both players play optimally. Let's explore a more general scenario with piles of varying sizes, piles equals 3, 4, 5. The key to solving this lies in the concept of the Nim sum, which is the XOR of all pile sizes. In this case, calculating the XOR gives 3⁴ to the power of 5 equals 2. Since the result is not 0, it indicates that the first player has a winning strategy. The exact moves depend on the game state, but the important takeaway is that the first player can always maneuver the game into a position where they maintain an advantage and eventually win. This demonstrates how the Nim sum provides a reliable way to determine the winner in games like Nim. The concept of the Nim sum is central to understanding the solution. When the Nim sum is 0, it indicates that the current player is in a losing position if the opponent plays optimally. On the other hand, if the Nim sum is non-zero, the current player is in a winning position and can make moves to ensure their victory. By strategically choosing which pile to take stones from, the player with the advantage can always force the game into a configuration where they maintain control. This is the mathematical foundation behind determining the guaranteed winning strategy in the game of Nim. In this problem, we are tasked with determining whether the first player can secure a guaranteed win in the game of Nim. To understand this, we start by exploring potential approaches, beginning with the brute force method. The intuition behind this approach involves simulating every possible sequence of moves for both players. By recursively considering all valid moves, we could theoretically identify a strategy that forces the opponent into a losing position. However, a key limitation of this approach is the rapid growth in the number of possible states as the number of piles and stones increases. Specifically, the computational complexity is exponential, k to the power of m, where k is the average number of stones per pile, and m is the total number of piles. This means that even for moderately large inputs, the brute force method becomes computationally impractical. While conceptually straightforward, this approach is not feasible due to its inability to handle the problem's scale efficiently. To address the inefficiency of brute force, we turn to a mathematical insight rooted in combinatorial game theory. The game of Nim has a well-established solution based on the concept of the Nim sum, which is the XOR of all pile sizes. This mathematical property reveals a critical insight: when the Nim sum is 0 at the start of a player's turn, that player is in a losing position, provided both players play optimally. Conversely, if the Nim sum is non-zero, the current player can guarantee a win by making a move that forces the opponent into a losing state. The beauty of this approach lies in the properties of the XOR operation, which inherently captures the parity relationships between piles. This allows us to determine the winning or losing state in constant time for each turn. The computational complexity is just O(n), where n is the number of piles, as calculating the nim sum requires only a single pass through the pile sizes. This method is both elegant and efficient, avoiding the exhaustive exploration of states required in the brute force approach. Given the options, the XOR-based mathematical solution stands out as the optimal strategy for solving this problem. It is highly efficient, with a time complexity of O(n), making it well suited for handling large inputs. Additionally, the simplicity of the approach rooted directly in game theory eliminates the need for complex data structures or recursive algorithms. Another key advantage is its guaranteed accuracy, as the solution is mathematically proven to correctly determine the winning or losing state. When comparing the two approaches, brute force, while simple to understand, is computationally infeasible for larger problem sizes due to its exponential complexity. The XOR solution, on the other hand, is elegant, efficient, and scalable, effectively addressing the problem's requirements. This makes it the clear choice for implementation, ensuring both correctness and optimal performance in all scenarios. In the game of NIM, players take turns removing stones from one pile, and the player unable to make a move loses. The challenge is to determine if the first player can guarantee a win. The solution revolves around the nim sum, which is the XOR of all pile sizes. If the nim sum is 0 at the start of a turn, the current player is in a losing position, assuming optimal play. Conversely, a non-zero nim sum means the current player can force a win. To calculate the initial nim sum, use the XOR operator iteratively across all pile sizes, as shown in the Python snippet provided. This forms the foundation of our algorithm for analyzing the game state. The computation of the nim sum is efficient, running in O(n) time, where n is the number of piles. The XOR operation works bit by bit, determining whether the total count of ones at each bit position across all piles is odd or even. Once the nim sum is calculated, its value directly informs the winning condition. If it is 0, the first player is in a losing position because any move they make can be countered optimally by the opponent. However, if the nim sum is non-zero, the first player can force a winning outcome. To simulate this, iterate through each pile to find one where removing stones results in a nim sum of 0. The optimal move involves removing precisely enough stones to achieve this, ensuring the opponent faces a losing configuration. By making this optimal move, the first player leaves the opponent with a nim sum of 0, locking them into a losing position. This strategy is underpinned by key properties of XOR. It is commutative and associative, allowing us to work with pile sizes in any order. Additionally, XORing a number with itself results in 0, and XORing a number with 0 leaves it unchanged. These properties simplify both the computation of the nim sum and the identification of optimal moves. The overarching goal for the first player is to always ensure the opponent faces a 0 nim sum. Edge cases are also straightforward. With one pile, the first player wins if it's non-empty. If all piles are empty, the first player loses. The algorithm's reliance on XOR makes it robust and efficient across various configurations. In terms of implementation, the algorithm works with simple data structures. The piles are stored in an array, enabling easy iteration and computation of the nim sum. Key variables include nim_sum for the cumulative XOR of pile sizes and optional variables like optimal_pile and stones_to_remove for determining the best move. The algorithm is computationally efficient, with a time complexity of O(n) for calculating the nim sum and finding the optimal move, and a space complexity of O(1) since only a few variables are used. For instance, given piles equals 3, 4, 5, we start with a nim_sum of 0 and XOR each pile size sequentially. First, XORing 3 gives a nim_sum of 3. XORing 4 updates the nim_sum to 7, and XORing 5 finally results in a nim_sum of 2. Since the nim sum is non-zero, the first player can guarantee a win. To find the optimal move, we check each pile. For pile 0, removing 2 stones achieves a target nim sum of 0, leaving 1, 4, 5. With this new configuration, the opponent is in a losing position. This algorithm effectively leverages XOR properties and the NIM-SUM concept to determine the winner and optimal moves in all scenarios. Its simplicity and efficiency make it a robust solution to the game of NIM. This solution to the game of NIM problem employs a key result from combinatorial game theory. The problem requires determining whether the first player has a winning strategy given the sizes of the piles of stones. The can-win-NIM function begins by initializing XOR_sum to 0. This variable will hold the XOR of all the pile sizes. The XOR operation is crucial in the NIM game because it helps determine the winning strategy. For each pile in the list piles, the function updates XOR_sum by performing an XOR operation between XOR_sum and the current pile size. This builds the cumulative XOR of all pile sizes. The final decision relies on the value of XOR_sum after processing all piles. If XOR_sum is not 0, it indicates that the first player has a winning strategy, assuming optimal play. If XOR_sum is 0, the first player cannot guarantee a win if the second player also plays optimally. This algorithm is efficient, with a time complexity of O(n), where n is the number of piles, since we iterate through the list once. The space complexity is O(1), as we use a fixed amount of additional memory regardless of the input size. The solution is both concise and optimal for this problem. This is the Java implementation of the game of NIM problem from LeetCode, number 1908. It replicates the Python logic by computing the XOR sum of all the pile sizes and determining if the first player can win based on whether the XOR sum is non-zero. Key differences include the use of Java's primitive types and explicit loop constructs for array iteration. The implementation adheres to Java conventions while maintaining the algorithm's simplicity and efficiency. The problem we're solving is called the game of NIM. In this game, we have an array called piles, where each element represents the number of stones in a pile. Players take turns removing stones from any one pile, and the player who cannot make a move loses. To determine the winner, the solution relies on the concept of the XOR sum. The key insight is that the XOR sum of the pile sizes can tell us whether the first player has a guaranteed winning strategy. If the XOR sum is non-zero at the start, the first player can force a win with optimal play. On the other hand, if the XOR sum is 0, the second player has a winning strategy. This is based on the mathematical properties of the XOR operation, which helps us analyze the game's parity of moves. Let's look at a simple example with one pile to understand this better. If piles equals 3, we initialize XOR_sum to 0. Then, we compute the XOR of the pile sizes. For the only pile, which is 3, we calculate XOR_sum equals 0(3), resulting in 3. Since the XOR sum is non-zero, the first player can win. The intermediate states clearly show the calculation. We start with XOR_sum equals 0, and after processing the pile, we get XOR_sum equals 3. The output for this example is true, meaning the first player has a winning strategy. Now, let's explore an example with two piles to see how the XOR sum behaves when we process multiple values. If piles equals 1, 2, we start by initializing XOR_sum to 0. Then, we compute the XOR of the pile sizes one at a time. For the first pile, which has 1 stone, we calculate XOR_sum equals 0(1), resulting in 1. Next, for the second pile, which has 2 stones, we calculate XOR_sum equals 1(2), resulting in 3. Since the final XOR sum is non-zero, the first player can still win by playing optimally. The intermediate states illustrate this step-by-step process. Initially, XOR_sum is 0. After processing the first pile, it becomes 1. Then, after processing the second pile, it becomes 3. The output here is again true, confirming that the first player has a guaranteed winning strategy when the XOR sum is non-zero. Now let's consider a slightly more complex example with 3 piles to see how the XOR sum changes in a balanced game. If piles equals 1, 1, 2, we begin by initializing XOR_sum to 0. Then, we compute the XOR for each pile step by step. For the first pile, which has 1 stone, we calculate XOR_sum equals 0(1), resulting in 1. For the second pile, which also has 1 stone, we calculate XOR_sum equals 1(1), which brings XOR_sum back to 0. Finally, for the third pile, which has 2 stones, we calculate XOR_sum equals 0, resulting in 2. Once again, the final XOR sum is non-zero, which means the first player can win with optimal play. Let's look at the intermediate states. We start with XOR_sum equals 0, then it becomes 1 after the first pile, returns to 0 after the second pile, and finally becomes 2 after the third pile. The output for this example is true. This example highlights how the XOR operation captures the parity of the game, and the algorithm efficiently computes the result in O(n) time by iterating through the array once. If the XOR sum is non-zero, the first player can force a win, otherwise, the second player has the advantage. Here, we're analyzing the time complexity of the given code. The main operation involves calculating the XOR of all elements in the input list, piles, and then checking whether the result is non-zero. First, the for loop iterates through each element of the list. If the list contains n elements, this step requires O(n) time since each element is visited exactly once. Next, for each element, the XOR operation is performed. This is a constant time operation, O(1), and since it's performed once per element, the total time for XOR operations across the list is also O(n). Finally, there's a comparison step where XOR_sum is checked against 0. This comparison is a single operation and runs in constant time, O(1). Combining these steps, we get the individual time complexities for iteration, XOR operations, and the final comparison. When we add these components together, the iteration contributes O(n), the XOR operations contribute O(n), and the final comparison contributes O(1). Among these, the dominant term is O(n), so the overall time complexity of the algorithm is O(n). Now, looking at the space complexity, the input list piles is provided to the function, but no additional memory is allocated to store copies of this list. The function processes the list directly. Additionally, we use a single auxiliary variable, XOR_sum, to keep track of the cumulative XOR during the traversal. This variable requires only constant space, O(1). Since there are no other data structures or memory allocations in the implementation, the overall space complexity remains O(1). Now let's consider the best, average, and worst-case scenarios. Regardless of the input, the algorithm always iterates over the entire list, performing the XOR operation for each element. There are no conditional checks or early exits that depend on the specific structure of the input. As a result, the time complexity remains O(n), and the space complexity O(1) for all cases, best, average, and worst. This consistency makes the algorithm very predictable in terms of its performance. Let's compare this with a naive or brute force approach. A brute force method might involve simulating all possible game moves and outcomes for the first player. This would require generating all possible game states and evaluating each one recursively. The time complexity of such an approach would be exponential, approximately O(2), sum of piles, due to the sheer number of game states that need to be explored. The space complexity would also be high, as the recursion stack would grow with the depth of the game tree. In contrast, the current algorithm optimizes this drastically by leveraging the XOR sum concept. It determines the winner in a single iteration of the list, reducing the time complexity to O(n), and the space complexity to O(1). This improvement is achieved because the XOR operation is a constant time, O(1), bitwise operation regardless of integer size. By iterating through the list once and performing this efficient operation on each element, the algorithm achieves its optimal complexities. Let's explore some common mistakes that can trip up candidates when solving the game of NIM. One frequent misunderstanding is about the XOR rule. Many assume the winner is based on the total number of stones across all piles, but in reality, the key lies in computing the XOR of all pile sizes, which we call the NIM_sum. If this NIM_sum equals 0, the first player cannot win if both players play optimally. Another mistake is neglecting edge cases, such as scenarios with a single pile, all piles containing just one stone, or when all piles are empty. These edge cases can lead to errors if not explicitly tested. Overcomplicating the solution is another pitfall. Some candidates try to use dynamic programming here, but the XOR-based approach is already optimal at O(n). It's also important not to confuse a winning move with a guaranteed winning strategy. Just because the first player can make a move doesn't mean they can force a win. Lastly, remember that not every problem instance is winnable for the first player. A complete solution must consider cases where the second player has the advantage. To succeed in interviews, it's crucial to understand the XOR operation and its properties. Since XOR is both commutative and associative, it's the perfect tool for combining pile sizes in this problem. You should practice explaining why a nim_sum of 0 leaves the first player with no winning moves under optimal play. This problem also introduces foundational ideas in combinatorial game theory, and recognizing the XOR pattern can help you solve a wide array of related problems. Interviewers often test your ability to think beyond the standard rules by asking how strategies would change if variations were introduced. For example, what if players had to follow a specific sequence when removing stones? Finally, be ready to discuss XOR intuitively. Understanding why XOR works mathematically and how it influences parity in the game demonstrates both problem-solving skills and a deeper grasp of the underlying concepts. There are several related problems worth exploring to deepen your understanding of combinatorial games. LeetCode 292, the NIM game, is a simpler version involving just one pile, which can be a good starting point. LeetCode 877, the stone game, is another interesting problem, though it relies on dynamic programming rather than XOR. Similarly, LeetCode 1025, the divisor game, introduces number theory concepts while still focusing on guaranteed wins. Finally, LeetCode 1140, Stone Game 2, builds on the stone game with added complexity and strategy, making it a great challenge for refining your skills further. Now let's consider alternative approaches and their trade-offs. One option is brute force simulation, where you simulate every possible move for both players to determine the outcome. While this guarantees correctness, its exponential time complexity makes it impractical for large inputs. Another approach is dynamic programming, which is useful for variations of NIM that have additional rules or restrictions. However, DP solutions tend to have higher time and space complexity, often n² or more. For certain variations, a greedy algorithm might work, although it's usually unsuitable for classic NIM due to the XOR-based strategy. Lastly, you can leverage bit manipulation for optimization in specific scenarios, especially when dealing with very large numbers. While not necessary for most cases, it can provide a performance boost under strict constraints. Thank you for joining me on this journey through LeetCode problem number 1908, Game of NIM. We reviewed the problem, explored the underlying theory, and discussed strategies for solving it. Make sure to practice similar problems to strengthen your understanding, and I hope to see you in the next session. Until then, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!